So this video is going to be a little more math intensive than the previous Trig primer video, but I hope that it is manageable. So the first thing I want to prove is I'm actually going to prove two things at the same time. The first one is I want to prove a formula that will allow us to calculate sine of x plus y and cosine of x plus y. And x and y here are both angles, as they tend to be with trig functions. And these end up being extremely useful for other things. So I'm going to start off by drawing a quick diagram. Okay, so this is a lot to take in. It's a complicated diagram, but I hope we can work through it. So the important thing here to note is that this triangle is going to allow us to calculate the trig functions of y. This triangle is going to allow us to calculate the trig functions of x. And then this triangle is going to allow us to calculate the trig functions of x plus y. Now I'm going to get rid of all that color so that the workspace stays a little clearer, because it's going to get a little cluttered. 1 second while there we go. Okay, so let's look at first sine of x plus y. Well, the sine of x plus y, oh, and this length is 1. The sine of x plus y is this length right here, right? Because if we think back, if I had that right triangle with theta here, and then 1 here, a and b, sine of theta was b, because the hypotenuse was 1. That is what I'm going for here. So sine of x plus y is length df. But df is made up of two smaller segments, and they are de and ef. So we're going to try to get the lengths of these segments in terms of x and y. And so the first thing we want to look at is what can we get? Well, let's look at our x triangle first. So if we look at this triangle, where from A to D to C, we have one side, and that side is the hypotenuse. So let's look at what sine of x is. Sine of x is length dc over AD. Well, AD is just 1, so it's just length dc. So I'll stick that there. That's sine of x. And this is a right angle. Okay. So that's useful, because now we can look at, well, we can also look at what the cosine of x is. So cosine of x is length AC over AD, which is just AC. So this length here is cosine of x. I'll draw that in a different color so it's not as confusing. second. I really need to change the software that I use. That length is cosine x. So now we're sitting fairly pretty to get CB. Why is that? Well, notice that that FECB, that shape, is a rectangle. So CB is the same as EF. So this is also CB. Well, let's look at now the sine of y. Sine of y is length CB over AC. But we've already found AC. AC is the cosine of x. So length CB over cosine of x. And then multiplying both sides by cosine x, we get length CB is cosine of x times the sine of y. And so that is one of the lengths that we need. That's the EF length, because EF and CB are the same length. Now let's look at DE. It's good. It's a little trickier, but it's still manageable. So the important thing to note here is that AB is a horizontal line. And so is EC. So what that means is that if this angle is angle Y, this angle has to be Y, because it's two parallel lines cut by a transversal. But if that's angle Y, then this angle is 90 minus Y. 90 degrees minus Y. So to make that DEC triangle have 180 degrees, this angle must be Y. So now, if we consider that small triangle in the top right, DEC, if we consider the cosine of Y, well, that is DE over DC. But DC, we've already found, is sine of x. So that means that DE is sine of x cosine of y. And that was the other segment that we needed. So sine of x plus y is equal to DE, but DE is this, and then plus CB. Oh, hold on. I didn't mean to put a plus there. And then plus this guy. So in general, if you have sine of the sum of two angles, you can decompose it this way. And now for cosine of the sum of angles. We've actually already done a majority of the work. So let's look at it in terms of segments. So cosine of the sum of angles, that's equal to AF. But AF can be decomposed into AB minus FB. Now, if we look at AB, we can get that using the cosine of y. So cosine of y is AB over AC. But we found a little while ago that AC is cosine of x. So we get AB over cosine of x. which means that AB is cosine x cosine y. Now for BF, or FB, we need to look back up at this triangle DEC up here. Now that's a little cluttered, so let me draw the triangle again and I'll just fill in the values that we already know. So we got y, a right angle, sine of x, and that's really all we need. Because this is length EC, but this is the same as FB. So it's the same as the length we need. Now let's look at what the sine of y from this triangle is. Well, its length FB, or EC, same, over DC. But DC was sine of x. So that means that length FB is sine of x, sine of y. And so now we have the two lengths that we need. We have AB and we have FB. So if I plug those in, we get cosine x cosine y minus sine x sine y. And so let me just make a little bit of room. I'm going to rewrite those, and then we're going to prove a couple more identities. So we've got sine of x plus y equal to sine x cosine y plus cosine x sine y, and the cosine of x plus y is equal to cosine x cosine y minus sine x sine y. So what does cosine of 2x equal? Well, this is cosine of x plus x, so I can apply the cosine formula. We get cosine of x times cosine of x minus sine of x times sine of x. And so what we end up with is cosine squared of x minus sine squared of x. But in the previous video, introing trig, I showed that sine squared of x plus cosine squared of x equals 1. And so we can rewrite this in two different ways. Sine squared of x is 1 minus cosine squared of x, and cosine squared of x is 1 minus sine squared of x. If we take each of those and plug them into here separately, we get two more forms for cosine of 2x. The first one is 2 cosine squared of x minus 1, and the other one is 1 minus 2 sine squared of x. And these formulas end up being extremely useful when you have an angle that you either want to double for some reason, or you want to cut it in half. So let's look at this one really quick. So cosine 2x is 2 cosine squared x minus 1. So let me solve this for cosine of x. I'm going to add 1 to both sides, divide by 2. So cosine squared of x is 1 plus cosine of 2x over 2. And then to get cosine of x, we just take the square root. Now, an important note here is that realistically, x can be anything in here. it's not limited to a specific range of angles. So it can be negative. But for the uses that we're going to apply it to, at least initially, we don't really have to worry about that a whole lot. But if you're going to generalize some of these ideas, you do need to be careful about that. Now, let's focus on that formula now. Cosine 2x is 1 minus 2 sine squared of x. Again, I want to solve for sine of x, so we get sine squared of x is 1 minus cosine of 2x over 2. After you've done the algebra, and so then by taking the square root, sine of x is the square root of 1 minus cosine 2x over 2. And again, the sine of x can be negative, so we'd have to account for that. But with the angles we're going to be dealing with, that's not really a problem. So these two formulas are important as well. So these two, and then these three up above, are extremely important formulas. So it's useful to memorize them if you're going to be using trig more than a couple of times. And you don't want to have to look them up every single time you need them. But that, unless your professor tells you can't, you can usually look them up somewhere. So now that we've got these identities, we can talk about the golden ratio and how it applies to pentagrams.